Hello everyone, welcome to tutorial number 10 for EC457A. So the topic of this tutorial is reinforcement learning and specifically we're going to focus on Q learning. I'm going to explain to you the algorithm for Q learning and different hyperparameters, and after that we'll move on to uh, Google Collaboratory in order to check the algorithm performance in a code and how to implement environment for the algorithm as well as the agent, AQ learning agent. So, as an introduction to reinforcement learning, um, the figure in the right hand side shows the relationship of artificial intelligence, machine learning, deep learning, reinforcement learning, and deep reinforcement learning. So as you can see, reinforcement learning is a subcategory in machine learning, which is itself a subcategory in artificial intelligence. And the part where deep learning and reinforcement learning overlap is the deep reinforcement learning, which will be the topic of the next tutorial in which I'm going to demonstrate the deep Q network. All right. So, this figure shows the agent environment interaction in a Markov decision process. So, agent takes an action or takes a step and in the environment, and that step results in a state, a new state, and a reward. So, this is the reward, and this is the next reward and next state. Now, next reward and next state become the current reward and state, based on which the agent chooses another action to interact with the environment. So this is a typical interaction figure that happens between agent and the environment in reinforcement learning. All right. This tree actually summarizes different algorithms in reinforcement learning. So, reinforcement learning algorithms are like in bandits and MDP, Markov decision processes. And we have different algorithms for bandits like action value methods or gradient bandit methods. And for MDP, we have model based um, algorithms like dynamic programming, or we have model free algorithms like temporal difference or Monte Carlo algorithm. And they will like have more subcategories, for example, value based or policy based algorithms. So in this tutorial, we are going to check or go through the Q-learning algorithm, which is an off-policy value-based model-free algorithm. And for the next tutorial, we are going to check the DQN algorithm, which is also an off-policy value-based model-free algorithm. Okay, Q-learning off-policy TD control. So as I mentioned previously, we are going to focus on Q-learning algorithm. So Q-learning algorithm allows agents to learn optimal actions through trial and error. And it is model free because it does not rely on an explicit model of the environment. So we don't need the model of the environment. And it is value based because it focuses on learning the values, Q values, associated with different state action pairs. So each state action pair has a Q value, and they will make a Q table, which we will see later. So this is an off policy algorithm. It's called off policy because the updated policy is different from the behavior policy. We're not going to dive deeper into that. We just accept it for now. And it is a temporal difference or TD learning method because it updates its value estimates at each time step based on the observed rewards and the estimates of future rewards. And it tries to find the optimal policy, hence it is a control problem. So these are the definition of different expressions that you might see in the area of reinforcement learning, especially for Q learning, just to understand what does expression mean. Okay, so this is the algorithm for Q learning. The first step is to initialize a step size and a small value epsilon, then initialize a Q table for states and actions and arbitrarily except that the terminal Q value will be 0. And there will be no actions for the terminal state because the game ends at the terminal state. Then we need to go through a loop and initialize the states, a loop for each episode, and choose action from state using policy derived from Q, in which we are going to check the or use the epsilon greedy policy, which I will explain later. So take action A and observe the future reward and the future state, like the next reward and the next state. And then this is the main formula for updating a Q table. And this part is called a TD error, like temporal difference error part. And after that, we accept the future state as the current state and do that process again until S is terminal, until we have reached the terminal state. Okay, so here, what is alpha? You have alpha over here, and it is used also here for the temporal difference error term. So alpha is a step size parameter, also called learning rate in the literature of machine learning. It can either be constant or change over time. So we are going to consider a constant learning rate here in our algorithm. And what is gamma? It is the discount rate. It is between 0 and 1 and determines the present value of future rewards. So as you can see, gamma is used here in this parameter, which is also based on the future state. So in this case, if gamma is 0, it means that the agent is myopic or short-sighted. It only maximizes immediate rewards. But if gamma is 1, it means that the agent is far-sighted. It takes future rewards into account more strongly. What is an episode? So as you can see here, we are looping through each episode. So the agent environment interaction breaks naturally into subsequences. So episodes are subsequences, such as plays of a game or trips through a maze or any sort of repeated action. So we're looping through the episode, so that will be a repeated action. Each episode ends in a special state called the terminal state, in which the episode ends, followed by a reset to a standard starting state or to a sample from a standard distribution of starting states. So at the end of each episode, like each the last step of the episode, we need to reset the state to the starting state or a sample of from a standard distribution of starting states. Now, what is epsilon here? As I mentioned previously, we are going to apply epsilon greedy policy for action selection. So in order to select an action, we need to use a policy. We need to have a policy in order to select our actions. Here, for this algorithm, you can use other policies like epsilon soft policy, but we are going to check epsilon greedy policy. So epsilon is the probability of taking a random action in an epsilon greedy policy. So it's a trade off between exploration and exploitation. For example, with probability of epsilon, we are choosing a random action. So when our actions are random, it means that we are exploring the area more than exploiting what we think is the best action. But uh, after a while, we may find the best action, like the action that maximizes the Q value, which will be the best action. So we need to exploit that action because it gives us the best reward. So we are choosing the best action based on Q values with a probability of 1 minus epsilon. Also, we can decrease the value of epsilon over time or over iterations, loops for each episode, so that we are less exploring and more exploiting. For example, at some point, epsilon may become zero, so we will not explore the environment anymore for different to see the effect of different actions because we have found enough information and we need to exploit those information for the best action and only use or apply the best action that gives us the best result or the highest reward. So this is the epsilon greedy policy based on which we are going to take an action here and observe the R and the next state or S prime. And this is a Q table. So there are different Q values here as I mentioned earlier. Q learning algorithm is a value based method. So it works on the values of uh, Q values for different states and different actions. So this is a Q table for N states and M actions. Okay, so these are the references that I use for these slides. And if you want to start learning reinforcement learning, I suggest you check out this book. This is a very good book that you can study and to get familiar with the fundamentals of reinforcement learning. This is an excellent book, and you can, I think, find it online as well for free. All right. Now let's head to Google Colab and see the code. I'm gonna walk you through the code and explain different parts of the code to you and run the algorithm for an example. Uh, Before going to Google Colab, I want to mention that you can find a code here in this GitHub repository, and this is the link for that. And you will find it down below in the YouTube comment section. Uh, yes, you can use the code and run it and tweak different hyperparameters and see the results that you can get. All right. So this is the Q learning for random walk. Random walk is the example that you encountered in the slides. I think it was page 36. And I want to demonstrate how to use Q learning in order to solve that. So Also, I picked an example from this book. Again, this is the second reference that I mentioned earlier that you want to start on reinforcement learning. So this novel implements the Q-learning algorithm for the random walk environment. The first thing is to import the packages. Here we are using the gym like library, OpenAI gym library, which is a toolkit for developing RL algorithms or environments. So we need that to create our environment. And environment is that random walk uh, that I, that random walk game that we want to go through. So this is basically the example, the random walk. So you start from the state C. You can go right or left with rewards of 0, 0, 0. And when you are going right from the state E, you get a reward of +1. And this one is a terminal state. This is also a terminal state, but when you're going from state A to the terminal state on left, you get a reward of 0. So it means that the terminal state on the right is what we are looking for to train the algorithm to find the terminal state on the right. Also, you can change the environment and change different these rewards to different values to like make the game somehow harder or easier for the agents to learn. So the first step is to create the environment. We need to have an action space. This create two. It means that we have two values for our actions: 0, which means go left, and 1, which means go right. Then we need an observation space, which is the state space. So somehow they refer to it as an observation state, and sometimes they refer to it as an observation state, and sometimes they refer to it as the state space. So we have here four states. Uh, this is the first one. Sorry, we have here seven states. This is the first one, and this is state number 7. So we can name them with numbers. This can be 0, A is 1, B is 2, C is 3, D is 4, 5, and the terminal, like on the right, is 6 in the language of in Python language, because it starts indexing from 0. So 0 to 6, total of 7 states in our observation space. What is the initial state? Initial state is 3. 0, 1, 2, 3. So C is the initial state because the example says they start from the state C. We need to define a function called step. Step is a function that takes the action and observes the reward and the next state. Basically, implementing that part of code that we need to take an action in the environment and get the future reward and state. So actions are 0 and 1. 0 means go left, 1 means go right. Rewards are +1 when terminating on the extreme right here, and 0 otherwise. Okay, so we need to define the actions, the rewards for these states. For example, if the action is 0, it means go left. Because our states are based on numbers like 0, 1, 2, 3. It means that when you're going left, you're decreasing one value from the state. So when you're going from C, which is 3, to B, which is 2, it means 3 minus 1, it's 2, the next state. And if you end up in the like left terminal state, extreme state, the reward will be 0 and done will be true. It means that the game or the episode is done, is finished. Otherwise, if we are not in the extreme left, reward will be 0, and we will not be done. The game is not finished yet. Now, if we move right, we need to add 1 to the state. For example, if we are moving from C, which is state number 3, to D, which is state number 4, so we're moving right, we're adding 1 to it. So we are in the next state. And if that state is the extreme right terminal state, the reward will be 1, because when we are moving from E to the extreme right state, the reward is 1, and the game is finished. So done is true. Otherwise, the reward is 0, and the game is not finished. And we are returning state, reward, done, and info. And we are not using info here, but maybe some more complicated environments. This render here also is for visualizing the environment. So we're not using this one here as well. And reset. So we need to reset the environment for a new episode. So when an episode ends, for the new episode, we need to reset the environment. As you probably remember in the slides, I mentioned that for the explanation I provided for the episode, I mentioned that we need to reset the environment to a starting state. So, for example, when the agent terminates here or here, for the next episode, we need to initialize this state and reset the environment. So the agent again starts from C. So yes, we are setting the state for the new episode to the initial state, which is 3, which means C. And the new episode begins after that. Also note that we are using env from the OpenAI gem in order to create this environment. All right, after that, it's a Q learning algorithm or Q learning agent. There's some explanations that you can go through, and this is also the algorithm. I extracted this information again from that book that I mentioned, the second reference in the slides, and you can refer to that for more information. All right, now let's implement this algorithm in Python code. So these are agents. Some initial values. We need to initialize alpha, the subsize parameter, epsilon, probability of taking a random action in an epsilon greedy policy, gamma, discount rate parameter, year, or discount factor, state space, action space, and number of actions. Then we need to initialize the Q table, as mentioned in here. Initialize Q as A, which is this part, and we are initializing every value to 0. So every state action pair is initialized to 0. So what is the policy? We need to define a policy as a function. The policy is like the strategy that we want to take based on which we want to take an action. So here we are implementing the epsilon greedy action selection policy. As a function, it only gets the state and updates the Q values and gets the Q values, and based on the Q value chooses the action. So as we mentioned earlier, here we are implementing the epsilon greedy action selection policy. We are choosing a random value here, and epsilon is if epsilon is greater than that random value, it means we want to explore more. So from the space of the like from the action space, we are sampling an action randomly. Therefore, this action can be either 0, go left, or 1. But if this is not true, like epsilon is less than a random value, it means that we are choosing the action, the greedy action, that exploits the environment, that is chosen based on the best Q value, that provides the best reward. And after that, we return that action as a next action for the agent to take in the environment based on the values that the agent can, based on the value of the best value in the Q table. All right. Um, this part actually is based on the state. So based on the current state, we have two actions, and we choose the best. Mm, like we actually get the Q values for that state for those actions, and get the maximum argument of that as an action. Like the action here can be 0 or 1. The one that has the greatest Q value provides the best reward. Yes, that part was in the slides. I don't have the picture, the image here of the epsilon greedy policy. Okay. After that, after selecting the action, we get a new state as prime. The reward for that, we have the previous state and the action that led us here to this reward and the new state. And we need to update the Q table based on this formula, which is basically this one over here. So this is gamma, this is max Q value minus self Q, and then we multiply this delta, which is the TD error. I mentioned here that this term here is the TD error multiplied by alpha plus the previous Q value that will result in the new Q value. So here we're updating the Q table. And after that, we need to decrement, well, actually, it's not necessary, so it's optional, but it's better to decrement the epsilon. So over time, the exploration tends to exploitation. We have explored enough, and now we have found the best action in the best action in any state, and we need to exploit that action to get the best reward, the highest reward each and every time. So, yes, here, if epsilon is greater than 0, use this formula to decrease it. Otherwise, epsilon is 0 and we are only exploiting. So, this is to decrease the probability of taking random action and ensure convergence with epsilon greedy policies. This is because as the action value estimates change toward the optimal values, the need for exploration decreases and more exploitation is needed. All right, so this is the main part of the code. This is a helper function which prints the Q table for each episode. I'm not going to go through that. Just know that this one is left terminal, this is state A, and this is the right or extreme right terminal. Okay, the main part of the code here. We have our environment. We have action space from the environment. We get the action space, which is zero, either zero or one. Number of actions is two. State space is the observation space of the environment. Now we need to initialize the hyperparameters. Alpha is zero point 0.1, epsilon is 1. So we start from 1, uh, which means that we are exploring because any random value that you select from the range of 0 and 1 here will be less than the epsilon at the beginning because in the beginning epsilon is 1 and we will for sure explore the environment. But over time, we will decrease the epsilon to exploit the best actions. And the discount rate parameter discount factor is 0.99. You can change these hyperparameters to see uh, what sort of behavior the agent shows in this environment. Number of episodes, let's go with 100 episodes or 100 episodes or games. And this is the main loop for the environment. So for episode in range of 1 to 100, so this part of the code is actually implementing this one loop for each episode. So state is from the environment reset. Environment reset, the thing that environment reset does is that here sets the state to the initial state, which is 3. Also, agent takes this parameter to create a new agent. I think I forgot to mention that. And set down to false because we are starting the game. The total reward is 0, step 0, and this is the actions taken. Okay, while not done, while the environment, the state is not like terminal, which is the second loop here, a loop for each step of episode. Env.render, so we're not using that because we're not visualizing the environment. Action. So it means that from the class agent, which is now an object, or agent is an instant of the class, a Q-learning agent, use the policy method into of that instant that gets the current state and produces an action. We get the action and we apply that action in the environment, like step action, and that action in the environment, that action of the agent in the environment results in a new state S prime, new reward, done. Either the game is finished or not, which means are we in a terminal state or not? And after that, we need to update the Q values using the state, action, reward, and the new state, and set the new state as the current state for the next game. Like for the next step, not for the next game because we are in the same episode, but for the next step. And add the rewards, add up the rewards to get a total reward. And when you're done with the first game, or the steps are done and the game is finished, decrease the epsilon for the next episode. And also env close, I believe, closes the visualization environment that render opens. And this is a plot part. Okay, let us run this and see what happens. Yeah, everything seems good. So, for the episode one, for the first game, the total reward is one. It makes sense because the only reward that we have um was is one when we are moving right from state E to the terminal state on the far right, like extreme right. And it took the agent 9 steps to get there. So the first action was zero. The agent went left. After that, the agent went right, then went right, then went left, right, right, left, right, right. Ended up in the terminal state. So 9 steps, 9 steps. And this is the Q table. And these are the Q values. Q value pairs for each state: state 0, left terminal, state 1, A, and state 6, right, extreme right terminal point or state. And action 0 is going left, action 1 is going right. So these are the Q values. And this value is just has been just updated after the first episode. As you remember, we initialize every value to 0. And in the next episode, the agent um, reached to the terminal state after 3 steps: right, right, right. So as you can see, the best course of action for the agent when the agent starts from C is to take the right, uh, like road or path, and then the right one, and after that the right one, and gets a reward of one, and the game ends here. So this is the best. Like best action here is to go right. The best action here is to go right, and the best action here is to go right and end the game. So after 3 actions, the agent reached the terminal point, and the Q values got updated. So we have episode 3, episode 4, and so on and so forth up until the last game, which is episode 100. And these are the values of the Q table. And for a plot. Okay, so this is total reward per episode. We had 100 episodes, and as you can see, after like episode 50 something, because we are decreasing the epsilon, it means that we are exploiting the environment. It means that in each state we have found the best action. So the total reward is 111 after like episode 50 something. So it means that the agent learned the best actions in each state, and the epsilon is has been decreased, and it's more exploiting the best action that provides the highest mm, reward rather than exploring the environment. So this part had some exploring because epsilon started from 1 and started decreasing from there. So we explored the environment a little bit. So we also had 0 rewards. It means that uh, mm, the agent ended up in the left side terminal, like extreme left terminal, and this one ended in the right, extreme right terminal. So the agent got a reward of 1. You can also compare this with like changing the environment in a way that, for example, over here, where is the Yes, here. So we can say that if the agent was here and moved to the left and ended up here, instead of 0, let's give the agent a reward of -1. Like, let's penalize the agent instead of rewarding the agent. So here, left terminal state, let's say it's -1. Okay. So when the agent ends up in extreme right, it gets 1. And when ends up in extreme left, it gets -1. Yes. So, um, instead of 0, we have -1 here. So it means that at these points, the agent ended up in the extreme left terminal state. But most of the time, the agent could find the terminal that we are looking for, the extreme right terminal. All right, I suggest that you play with this variable, hyperparameters, and like check the effect of different values of the hyperparameters and see if you can like get to the best actions in a less amount of episodes. Like in 50, as you if you remember in the previous game, we reached the best actions after 50 something episodes. See if you can like play with these hyperparameters and get to their like with less episodes. Like it means that the agent learns the environment and best actions in the states in each state in a less amount number of games. All right, so that's it for today's tutorial. I hope you enjoyed it. Until next time.